Okay, this is the last of 5 recordings on describing distributions, and in this particular video we're going to talk about another way of visualizing distributions called box plots, and show that box plots are based upon percentiles of the distribution. Okay, so again I'll go ahead into slideshow mode. Okay. So box plots, you'll see where the name comes from in a moment. It's really a box. And I'm just going to show you one and describe how they actually work. Okay, so we have, well, in fact, let me set up a pen option. Okay, so notice we have some scale of measurement. So this would be the aluminum lithium data, and it is measured on a scale of KSI, so that's our scale, and it runs from about 75 to 100 for this particular data. And notice that a box is constructed, and the ends of the box correspond to the 25th and 75th percentiles. So the length of the box is the interquartile range. So the length of the box directly relates to the spread or scatter in the data. And then there's a solid line inside the box, and this is the location of the median. Okay, this diamond or centered diamond we're going to ignore for now, so we're not going to pay any attention to it at the moment. We'll come back to that later on in the course. Now notice the box describes the distribution for the middle 50% of the data. But then notice that these whiskers come off on each end. Okay. Well, what do they represent? They represent the tails, but they have a special interpretation. First, using some statistical theory, any observation that is more than 1.5 times the interquartile range away from each end of the box is a potential outlier. In other words, it's an unusually extreme value. So I'm going to just basically crudely draw in what I'm going to call the outlier fences. They're typically not shown on the plot, and these are drawn at 1.5 times the IQR, okay, from each end of the box. And similarly, we'd have one at the other end. So any observation that goes outside of these imaginary boundaries, again, they typically don't show them on the plot because they make the plot rather noisy. They're simply plotted as separate points. Those are suspect. They may be fine, but they are suspect points. There's 2 that are unusually low, 1 that's unusually large. So how do you construct the whiskers? Well, you draw the whiskers from each end of the box to the point that is farthest away but lies within the outlier boundary. So in each end of the box, we've drawn the line to the farthest point from each end of the box that lies within the outlier boundary, because we consider this confidently to represent the distribution of observations. So if the 2 whiskers are about the same length, this indicates that it's a symmetric distribution, and typically when that happens you'll also see the median is very close to the middle of the box. Okay, so this is called an outlier box plot, simply because it is a way to detect outliers. As a general rule, Observations that are more than 3 IQRs away are very strong outliers. Observations just generally don't scatter that far away from the middle 50% of the data. Okay, so here's the box plot done in JMP. We'll do this in JMP right at the end. It's shown by default, and it's essentially the same plot you saw on the other slide. And you can see the distribution is symmetric. Okay. Well, let's go to JMP. No, we'll show a couple of topics while I'm there. Let's see. Okay, so there's the aluminum lithium data. And first we'll go to the Analyze menu, look at the distribution. Again, I'll only look at KSI. Okay. And we see the box plot. And just as a reminder, when you use JMP, they have the so-called in-context help. So if you're looking at the box plot and there's something about it you don't really understand, or any other JMP report, just go to the top to your blue ribbon, go over to your cursor bar, and grab the question mark. Bring it down, put it on whatever you don't understand, and they will take you to JMP help, and then you can read through JMP help and it'll give you a description of various distributions of things. In other words, you don't really have to know the term. You can use the question mark to help you find the information. Now, there's an important point about that outlier rule. Remember, any observation more than 3 interquartile ranges away from each end of the box is suspected as an outlier. That rule only applies to symmetric distributions. So if you have a skewed distribution, we cannot use the rule. So I'm going to illustrate that by using the delivery time data. So let's switch over to delivery time. And again, you may recall this is a skewed distribution. So again, we'll pull up the histogram and box plot. Okay. So notice, in this particular case, the median is not centered in the box. In fact, it is moved to the left because the bulk of our data is actually on the low end of the scale. And notice that the two whiskers are of very different lengths because, again, there's a long right tail. So the box plot would tell us this is a highly skewed distribution. And because it's skewed, our outlier rule doesn't apply. So we cannot assume those 3 or 4 larger observations are actually outliers. They may be perfectly fine measurements, so we wouldn't automatically look at them because they're beyond 1.5 interquartile ranges. We only use that rule when we look at symmetric distributions. Okay. So I'm going to go back to the aluminum lithium data and just explain one of the ways box plots are used quite frequently is to actually compare distributions to each other. Like, what if I have a set of different samples and I'd like to compare the distributions of the different samples? Well, here we have a scenario with the aluminum lithium data. There are 80 measurements, but they were collected in batches of size 10. So there are 8 batches. So that asks the questions, are the distributions different within each batch? Well, that's hard to say at this point. We'll come back to this later on with some more statistical methods, but for now, we'd like to look at a plot and at least try to compare the distributions. Remember, if this is a stable or in-control process, then that's producing these parts, then the batches should all be about the same. So we'll go to Analyze, Fit Y by X. I want to compare two columns. Okay. So KSI is the response, and batch is X. So I want to compare the KSI distributions for the different batches. Okay. So in JUMP we get this scatter plot. Spread it out. So you can see the scatter of observations for each batch. And there's a few things you can do in here in terms of display. The report menu contains a lot of options. We'll come back to many of them later on in the course. But some are display options. And one thing I like to do with these scatter plots where the X variable is nominal is to jitter the points a little bit. Basically, all it does is horizontally just put a little noise in the measurements. The reason is if you don't do that, the points overlay and it's really difficult to see the distributions. So I'm going to go up to the report menu, and the first option is quantiles or percentiles. So notice in the table down below, it gives us the statistics, including the quartiles, and the max and the min for each one of the batches. And then up above we get box plots. Again, the length of the box directly corresponds to variation. And then the horizontal line within the box is the median. Again, these are pretty small sample sizes within each batch. But if we look across this, there are some potential differences. Particularly, look at A and compare it to H. For H, the box is relatively short, and for A, the box is very long, so it looks like there could be a lot less variation occurring in batch H. And also notice the median is lower, and we can show this down below. The median, okay, for batch H is 142, and for A, it's actually almost 180. So there's a big difference in the medians. What about the interquartile range? Okay. Well, notice for A, the interquartile range is roughly a little over 80, about 83 KSI. So we take a look at H, it's about 21. So the variation in A is about 4 times that in H. So that leads us to suspect there may be differences going on in these batches, even though they should all be approximately the same. And then finally, in display options, again, we'll cover a lot of these options as we go along. There is a nice little option called Connect the Means. So I like to do this also when you're looking at what I call comparative box plots. And this just adds additional information because the blue line connects the averages. And once again, you can see in looking at this that the mean for A seems considerably different than H. So quite often this is how box plots are more often used in practice. People have sets of samples that are divided by possibly some variable. They were sampled on different days, different machines, different people, and you want to compare the distributions. Well, visually, box plots are a nice way to do it. Okay, so I'm going to go briefly back to the notes. And Everything I just discussed is in here about the comparative box plots. Okay. I won't cover this. The graph builder platform and jump will also do box plots, and since it's a drag and drop interface, it's pretty easy to use. Okay. And there's a skills practice. I might assign this later on as a homework problem, so we won't actually do it. And that concludes our discussion of describing continuous distribution.